I think we can start now. So before going forward, let me just maybe kind of clarify one issue that so came up in the last lecture, and then I'll see what's going on. So this is like the group theory. Underlying finance theorem. Okay, so this can be abstracted, and it's kind of nice to think about it in these terms, actually. So what do I mean by this is the following. Imagine you have a function f from a finite set x to c, this sort of complex valued function, and you want to compute this sum. Okay, so you just add them and then you compute them, right? But there may be many, many elements in x, and this may be a complicated task. But there is something, a situation, a scenario that helps to reduce the amount of computations. And that's where there is a symmetry here. So let G, okay, an action of G, of a group G.
Here, X is a discrete space.
Yeah, X is a finite set for that matter. Yeah, I will tell you in example what it came to, but I mean in this case it's just a finite set, and it's we have a X is a G space, but now imagine that this F is invariant under G. Okay, so G is the symmetry of F, and F is the G invariant. So this means F of Gx is equal to F of X for all G in G and X in X. Okay? Then what you can do, you can decompose X into its orbits. So orbit is space of X. So this is X. And then you can decompose this into its orbits, right? And then what happens is that on each orbit, F is constant. If you take orbits, F is constant on each orbit. And so this sum then, you can write it like this. Sum F of X, X belonging to X, is actually equal to sum F of orbits, O belonging to orbits of X. However, you have to multiply by size of that orbit, right? Because you pick a value here, we call it f of O for each orbit, but then there are so many other points that have same value. So how many size of the orbit? That many. And you multiply, and then this is this one, right? Okay, so now what happens in this case is that, of course, G acts on each orbit transitively, by definition, right? And G acts transitively. On each orbit. And so then we can use this orbit stabilizer theorem to reduce, to relate the size of the orbit, actually the orbit to the thing. So let, so to be precise, let stabilizer of X be equal to the set of all G belonging to G such that Gx is equal to X. So this is the stabilizer of a point X in X. Stabilizer of x in x. Then the orbit stabilizer theorem tells us the following. It just says the following thing, that this orbit, each orbit is actually in one-to-one correspondence with g divided by order of a stabilizer of one of its points, right? That O, each orbit, is in one-to-one correspondence with g divided by stabilizer of x. This is for any x belonging to this orbit where O is any orbit. Right? Okay, so this relation then tells us that we can actually say the size of O is order of g divided by order of the stabilizer, right? So then I can just say that we can just say that order of O that I needed here, size of O is equal to number of elements in G divided by number of elements in stabilizer of X. Now, this stabilizer we can think of as symmetries of this object X, because that means it doesn't move X to another point. It really keeps X fixed. So we can think of it as symmetries of automorphisms of X. So, or in fact, we can think of symmetries of this orbit itself, because we pick one representative, and so this is equal to order of G divided by order of automorphisms of O, if you want. Then here we can just say that, okay, here, so the formula then in this case gives me, so this is star, gives us that indeed the sum of f of x, x belonging to x, is equal to sum over orbits, order of g divided by order of automorphism groups of the orbit. Okay, and then I can divide on the left hand side by order of g, and then we get the formula. Then we get the formula that 1 over order of g sum f of x, x belonging to x, right, is equal to sum f of O divided by order of automorphism. O belonging to orbits of x. And this is some sort of abstract kind of Feynman's theorem, which can be applied in many other situations, but this is sort of abstract version of the theorem. Right? How we apply this, okay, so maybe I was not very explicit that I'm using this result last lecture, but actually that's what we are using. And so let me now look at what was x in the last lecture. In actual Feynman's theorem, x was x is the set of half edges of okay. To be precise, x is the set of pairings of half edges. Yeah, that's x is set of pairings of half edges. T. And So in that case, so this is like sigma, and f of sigma was the f sigma is the Feynman weight of the pairing. And G was a set of permutations of these pairings. That preserve the flower structure. And then that was so in that case, each orbit corresponds to a graph. Yeah, so then we obtain this formula, which we used, we derived and used in this couple of examples. So I think it's a good idea to always think in terms of this sort of situation. That's the group theory underlying the theorem. Okay. Yeah. Okay, so now we have to deal with another reduction, which is so you see, we are reducing from sum over pairings to sum over graphs. Now we are reducing further, summing over connected graphs and the free energy for that. So I already checked that in one example. Now it's time to prove the general theorem, which is not difficult at all. So the theorem is the following. So this discussion is free energy F equal to log Z. This is by definition, as we discussed in the last lecture. And summing over connected graphs. Sum over connected graphs. Okay. So to normalize things, we divide by Z0, which is determinant of root 2 pi over b as usual. Then z over z0 starts with constant term 1, and then there is a power series in G, which is 0 at 0. This is 1 plus h of G. This is a power series in G. I mean, G is G1, G0, G1, G2, up to G infinity, and h of 0 is equal to 0. Okay, so then the theorem is the following. Yeah, so log of z over z0. Maybe here I should call this log of z over z0 to be more precise. Log of z over z0 is equal to sum over all multi-indices, product of gi to the power ni, and then sum over gamma belonging to GC of n h bar to the power minus chi of gamma over order of automorphisms of gamma f gamma. But this means connected graphs which has an I-valent vertices for all I. Okay, so this is connected. This is important graphs with an I-valent vertex. So for each multi-index, we get this finite set because the multi-index is zero after a while. So it's only a finite number of ni's non-zero, and this is the Euler characteristic of the graph as we defined in the last lecture. Okay, so doing this just requires a couple of observations to prove. Okay, so there is this disjoint union operation of graphs. So if you have two graphs, gamma 1 and gamma 2, we can stack them together and create a new graph of this, which won't be connected, but we can do that. So we denote this by gamma 1, gamma 2, right? And then any graph, it can be uniquely decomposed into its components, right? So then any gamma, you can write it as gamma equal to gamma 1, K1. By this notation now, gamma 1, K1 means that it can have K1 component of type gamma 1 and K2 components of type gamma 2 and then KL components of type gamma L. So this is a bit like prime number decomposition for integers, actually, but there's no primality here. It's just connectedness, which is the idea, but there are the different types, right? Forget that. So these are non-isomorphic graphs. So these are non-isomorphic. Obviously, if they are isomorphic, we put them together under one heading like that. Then one thing we have to observe about this this decomposition, this operation is the following: that the Feynman weight of gamma, if gamma is equal to gamma 1, gamma 2, Feynman weight of this guy is the product of their Feynman weights. I mean, it's because we multiply or contract, basically. So this is equal to Feynman weight of gamma 1, Feynman weight of gamma 2. And also we have to understand automorphisms of this sort of thing in terms of automorphisms of the individual things and automorphisms of gamma, where gamma now is this one, right? Is first of all product of these automorphism groups to power K1, and then there is one thing. So this is product of yeah. So let me write it like this: automorphisms of gamma 1, L1, gamma 2, L2, gamma K1, sorry, K1, K2, gamma L, KL is equal to product of these automorphism groups. I mean, the order of these guys actually be K only. That's J from 1 to L. This guy, the power Li, or Ki, sorry. Yeah. Times Sj. Mhm. Yeah. So what is going on here? This is this J. Yeah. So here we are taking automorphism of this, but then when you stack them together, there is one group. Oh, here it should be J, perhaps. Okay, J. Yeah, and then you can also switch this. You see here you have gamma 1, gamma 1, gamma 1, K1 times, right? And then we can switch these guys, but why I have J from 1 to L? So this is J from 1 to L. Here is L. So this is there's a mistake here. I believe I should put this here. K, because I can switch these things still. So I should put K, J. Yeah. Right.
Sorry, what is S?
Sorry?
J? SKJ.
What is
SKJ.
SKJ? Oh, S is a symmetry group of
okay.
n letters, but here there are KJ, that's the number of letters, because we have K1, K2 repetitions at each time, and we have to take care of repetitions. We introduce symmetry. Yeah.
On the top is F gamma is F gamma 1 F gamma.
Yeah.
No. Here is this one.
Oh, no, on the
F
top.
gamma.
Or F gamma
No,
is
it's not
equal-
gamma gamma. F
Should
gamma.
be F.
What's that?
Oh, that should be F gamma and not gamma gamma.
Oh, F gamma. Oh, yeah. That's right. Yeah. So there. I thought you meant, right. So they're so close. Notation is kind of awkward. Sorry. Thank you. Yeah. Great. Okay, then, so these are the two things, preparations we need for the proof. Then, to prove, so, okay, so then we just say, then, take the original Feynman theorem. Original Feynman theorem. And this tells us, so first of all, just write Z over Z0, which is, of course, equal to exponential of the right-hand side of our formula. Of the star. So star is the original formula in the theorem that I erased part of it, unfortunately. So, but you have it in your notes. So star in the theorem, right? Because I mean, this guy is defined to be log of this, so this guy itself is exponential of that. And if you do this using these observations, you get that this is equal. That's this statement. I mean, here there are only connected, the sum is over connected graphs, because you can decompose everything into disconnected ones, then you're producing all disconnected ones by multiplying this, and this is exactly the operation of exponential. So basically what we are using is formulas like this, exponential of a, b plus b plus c, etc., is equal to sum ai over I factorial bj over j factorial ck over k factorial I plus j, I mean, I, j, k equal to 0 up to infinity. We have an expressions like that. So once you do that, then you're producing everything here. So yeah, it needs a little bit of thinking, but that's it. So, but this is a very important theorem. because it not only reduces the number of computations, but also leads to something beautiful called loop expansion. Any questions so far? Or? Okay.
Is it called free energy just because it's the log of the partition function, or does it have anything physical conserved quantity behind it?
Oh, there's a lot of physics behind free energy. It needs a lot of intuition in statistical mechanics, comes from that, and also even thermodynamics. This is one of the important potentials.
Yeah, like in this particular case, does it mean anything? Like,
No. But I mean, that's always like partition. But because our partition functions are very general, but it's always like this in a stat-mech, for example.
Is it related to?
So you have to ask.
Is this like related to Gibbs free energy?
Yeah. I believe this is what Helmholtz free energy or something like that.
Yeah.
I think this is what. Yeah, but yeah. So free energy. I actually let's discuss that after the class. Yeah, that's a wonderful topic. I love to engage into that. Yeah,
sure.
Yeah, we can discuss that. Okay. That's the energy that's really available and can be applied to change the system rather than the original energy, which is, yeah, anyhow. Okay, so the next topic is so-called loop expansion. So imagine you have a graph like gamma. Oh. Imagine you have a graph gamma, right? So it has a set of edges and a set of vertices, right? V is the set of vertices and E is the set of edges. Then you can do the following thing. You can form two vector spaces, linear combinations of vertices. I call it maybe RV. And then I can construct another vector space with the set of edges. I call it RE. And then I can define a map in this direction, D, which is the following. So you have to fix an orientation. It doesn't matter which orientation, but you just orient edges, fix an orientation. Okay. And then this map of each edge is equal to the original vertex of edge minus the ending point of edge. So this is the, it's called, V1 of E minus V2 of E. So this I call it V1 of E, this I call it V2 of E. You subtract.
How do we assign the direction? Because
Any way you want. It doesn't matter at the end. You can prove that actually. The calculation doesn't make any. Okay. So once you have that, so then here we are going from 0 and here we're going to 0. You can imagine we have something. Then we can define some groups here. So the first one is H0 of gamma, which is RV divided by image of V. Image of D. And the other one is just kernel of D. So H1 gamma is kernel of D. This is called the zeroth homology group, and this is the first homology. So these are a graph is only a one-dimensional object, so it has only two homology, and these are the two homologies. So homology groups of gamma. Okay, now you can easily see that this guy is the number of connected components of basically gamma, H0 gamma is equal to number of connected. I mean, for any topological space, this is basically number of past connected components of the space topology. Number of connected components of gamma. But then this H1 is the number of loops or cycles in gamma. I mean, these are intuitively defined usually, but here we can define it precisely. So H1 of gamma, number of independent, I mean, how to say independent loops or cycles in gamma. That's what H1 of gamma is. If you think about this, the kernel, how the kernel goes, in order for this to vanish, you have to end point and beginning point of a vertex have to come to each other, and similarly. So this you can convince yourself. Okay.
So if we have a space X,
Hmm?
if we have a space X such that we get, if we take the triangulation of it such
Mhm.
that it becomes this graph gamma, then is H1 the fundamental group of the space, or
Without it.
Okay.
If no, it's not true in general. Yeah, that's not true. Yeah. Okay. So, but for graphs, we have that. So then there is a simple lemma from linear algebra, simple linear algebra, that if you have a linear map like this, and it's C0, C1 vector spaces, and map like C0, C1 like this, or map B, then what happens is that dimension of C1 minus, I would say dimension of C0 minus dimension of C1 is equal to dimension of the homology minus dimension of this homology. I mean, this is a simple rank plus nullity theorem, basically. I encourage you to prove that using rank plus nullity theorem. Once you prove that, now this guy here, we define to be the Euler characteristic of the, I mean, dimension of C0 is the number of vertices minus number of edges, and the other one minus dimension of C1. So this is essentially what's exactly the Euler characteristic of the graph. So comes out to be equal to dimension of H0 minus dimension of H1. Right? Okay, now if we assume that the graph is connected, this number is 1. It has only one connected component. I mean, everything is just, this number is 1. So then it follows that Euler characteristic is equal to 1 minus number of loops. I mean, generators for the space for the loops. So we get that Euler characteristic. One minus loops. I mean, then because number of loops is either 0 or 1 or 2 is either a non-negative number, so this is always less than or equal to 1. It could be 1, it could be 0, but then in most cases it's negative. So that's what it is. So using this, then we can write log of z over z0 in a different form. So this is what I wanted to get from this simple discussion. So then it follows that log of z over z0 is equal to sum n product of gi and I as before, and then we have some gamma belonging to G CL. I'm just writing the formula again. But then we can just, the H power now we can handle better. So this is equal to H bar to the power L gamma minus 1 divided by order of R gamma F gamma. Remember, originally it was H bar to the power negative Euler characteristic, and Euler characteristic, this is number of loops, by the way. So this is the loop number. Okay, so now we can write it in terms of loops expansion. So this is equal to sum j from 0 up to infinity log. So there's some notation you introduce log z over z0 of j h bar to the power of j minus. I mean, we just because now we organize, we isolate h bar to power of j minus 1, where j is L of gamma, and then expand in terms of this h bar. Sorry. And then the coefficient we just say is the jth component of this, where j is the number of loops. Okay? Yeah. I mean, okay. Okay. And this is called the loop expansion. So obviously, if you have j equal to 0, you start with a negative power. So there is this h bar to the power minus 1 for j equal to 0. And there is this coefficient here. This coefficient is summing over trees now, right? Because there are no loops. J equal to 0 means that there are no loops. So this is sum over trees, right? Sum over trees. And then there is H0. And here is sum over one loop graphs, okay? Sum over one loop graphs. With plus, and then of course there is something two loop graphs, and so on. But the beautiful thing is that these two terms you can identify easily in terms of classical and semi-classical component information. And this is for most calculations actually these two are the most important somehow, giving complete. I don't know, physicists go sometimes to two loops, but that's in actual QFT calculation, this is a heroic computation. It takes so many graphs and so many diagrams which you have to renormalize. It's a huge deal. But I mean, these two things we can just at least say something about it now. Okay. Any question? So now we're going to identify this without actually summing over trees. This can be identified completely classically, and this also semi-classically can be identified without doing anything. Okay. Okay, so that's now the next task is to identify these first two terms in the loop expansion. Yeah. So the theorem is that this part is that indeed log zz0 the three component is equal to negative S of x0 and log zz1 is equal to 1/2 log of determinant of P over determinant of x double prime 0. But x0 is the unique critical point of S. So this is called the semi-classical contribution to the partition function, and this is exactly the classical contribution. Classical. And this is semi-classical. The proof goes, we just write down the expansion again. So, okay, I just say suffice and prove it for of x equal to 1/2 bxx. There's a quadratic part in the minus. Yeah, sigma gi bi x over I factorial I from 0 up to n. I mean, I just consider them for finite number of terms because in any practical problem, after a while, they're all going to be 0. I mean, usually you don't go more than quartic, but that's what we do. Okay. So then, so now let Z, as before, in our quantity that we are looking at this expansion minus T over 2 integral over B exponential. So this is like ZE now. Okay, so these two B's are very dangerous. So over box, let me put it like this box. For box, exponential of minus S of x over H bar, where box is a small box containing 0, containing the origin. And because this function, its second derivative, I mean, is non-degenerate positive definite, this is a perturbation of this. So then you can convince yourself that there is a unique, actually critical point inside this box. That's not difficult to see. So there exists unique critical point, which we call it x0. This box. Okay. Okay, now, which is non-degenerate actually. Now, then I have to use something that I haven't talked about it yet. I just alluded in the first lecture, but we will get to that soon. That's called the Laplace method, which I will go in detail about it. By Laplace method, these sort of integrals, we know that we can expand them in terms of some singular part, and then there is a power series expansion. That's thing. So basically, we know that Z over Z0. So let me write it like this. Z over Z0 is equal to, which is equal to exponential of minus S of x0 divided by h bar. I mean, this is the singular part is for h bar going to 0. It blows up or goes down, and then times I of h, where okay, so let me put it like this: times I of h, where I of h is the following expression. We know is determinant of b. Okay, so let me put it like this: determinant of b over s double prime at x0 to the power 1/2. Yeah. These are two matrices that are divided by each other. We take the determinant square root and then times 1 plus a1h plus a2 h2. So then there is a smooth function which is multiplied by that. That's the Taylor series of that smooth function. So this comes from the first lecture. But again, this Laplace method I will discuss in more detail soon. So we are allowed to write it like that. So then you take log now on both sides and see what is the log of this expression. You see. So if you take log of this, yeah. So from here, you get that log of z over z. So if you take log of this, you have to take log of right hand side. So the log of z over z0 is equal to now okay, minus s of x0 h bar minus 1. This comes from here because log of the product is the sum of the logs, and then this you get this part, the 3 contribution, and then the second part is plus 1/2, and this 1/2 log comes down, so it's 1/2 log of yeah, that's b over double prime x0 plus terms that have order 1 in h or higher. So I just write it as O of h, capital O. Yeah, these higher order terms are going to contribute here only, not here. There's a h0 here and there's h minus 1. And if you compare this with the original formula, that's the proof.
What happens to the A1 when you take the?
Sorry?
What happens to the A1 when you take the?
Or they come here because we are taking log.
Okay.
So they don't contribute to h minus 1 and h term, definitely. Yeah. You see, this multiplies quite often. I mean, it's okay. So, yeah, I mean, so remember that classical action. I mean, this equation delta x equal to 0, this gave us x0, right? This is a kind of classical solution of the problem. And s of 0 is the classical action that's extremized. And this comes from this expansion as well as the 3 part. But this part is not visible in the classical physics. This is the quantum phenomenon. It's called semi-classical though. But then these are purely quantum, other higher fluctuations, but then these are quite subtle. I mean, definitely very difficult to compute.
Like we are approximating the integral over R of t with some small box.
Yeah, that's right. So the thing is, yeah, that's a good. So the thing is, the remainder for the rest of the space, because formally we are computing over the whole space, is exponentially small. Actually, does not contribute anything to the expansion. So we can neglect those. It's like when you have a Gaussian, when you cut it in finite part, the remainder is exponentially small. So it's
Like the like 2 sigma.
sorry.
Like the 2 sigma bits which we take.
Yeah, exactly. It's something like that.
It's like the maximum contribution is near the point of interaction.
Yes. The most prominent contributions are from the classical thing, and that's the next one. Okay, I think I'm going to go for. Oh, there's a question here, by the way, in the chat. Yeah, sorry, you could have talked actually. Oh, there's an answer. Someone answered that yes, F equal to U plus TS. Indeed, that's the most important equation. So, Brett, can you send me your answer by email, please? And then I will forward it to the participants here.
Oh, perfect. Sure.
Thank you so much. Yeah, that's a great answer. That's what I was looking for. Yes.
Oh, cheers. It's fun to think of, so it's kind of cool. No problem.
Fantastic. Thank you very much. Yeah.
Thanks. Cheers.
Great. Yeah. So yeah, there's a great answer actually. Why this free energy? But there's a thermodynamic relation between the free energy and absolute temperature and entropy. Yeah. So that's so there is a competition between entropy and energy. And so in this, it is not that energy is minimized. It's free energy that's always minimized. If you allow entropy also does its game. So there's a subtle thing going on. It's quite subtle, actually. Okay, so if you allow me, I will just, because I want to get some momentum now, so I will prove this Cayley's theorem. I need 10 minutes to do that. Because this is one of the things that I advertise. So Cayley's theorem on a number of labeled graphs. Oh, labeled trees, I'm sorry. Oh, graphs, no. Labeled trees with n vertices. Okay, first of all, a tree, again, we know what the tree is. Means no loop, unconnected. So, okay, so first of all, there are no formulas for the number of trees with n vertices. But once you label them, there is this beautiful formula of Cayley. So let me tell you the issue. So for example, imagine an tree. If you don't label, you have only one tree with three vertices, just one unlabeled tree. Yeah. However, if you label them, so you have 1, 2, 3. But then you can put something else here, and then there's going to be a different tree. So you label 3 here, and then 1, 2. But then it doesn't matter if you put 2 here or there, because it's symmetric still. There's a labeled symmetry. And then you can put 1 here. 1, and then 1, 3. So there are 3, actually, in this case, labeled trees. And there are 3 of them. So you can see that the issue, if you label, you're creating more varieties because the incidence relation, the order relation is in the matters. Now, if you have, so this is n equal to 3. Now, if you have n equal to 4, for example, you will have 16 labeled trees. But I actually didn't count the number of unlabeled trees with 4 vertices, but it's much less than 16. So the theorem is that there are actually n to the power n minus 2 labeled trees with n vertices. That's what we want to prove. Okay, any question?
Is there at least an upper bound? Better than the number of labeled trees, like a smaller upper bound?
There must be. Yeah, there must be. They have been studied to death because these are also very important for practical applications of a lot of things. So, well, I don't know. That's a good question. Okay, so I can erase this and then write the theorem. So the theorem is that there are n to the power n minus 2 labeled trees with n words. I mean, so n here is bigger. Well, yeah. Actually, it can be 1 as well. Doesn't matter. Or still the formula is correct because 1 to the power 1 minus 2 is 1 still, which is 1 point. So okay, so there is actually there are many proofs of this, by the way. Many proofs. One proof is beautiful. You put this into one-to-one correspondence with the set of sequences of 1, 2 up to n minus 2. Okay, all numbers. So there's a kind of proofer coding of the tree. Yeah, but then there are other proofs. But now I want to give this proof by which is again this is from Ettinghoff's paper. So we set up actually a finite integral expansion, which is very similar to what we did before, except that we don't have any extra parameter z anymore. We just have this. So let's get this. So let s of x be equal to 1/2 x squared minus g e to the x. And we are interested in this integral e to the minus s of x dx minus infinity to plus. So here we have put each bar equal to 1. So Feynman's theorem tells me that, so rather loop expansion tells us that some Gn, some gamma belonging to Tn, 1 over order of morphisms of gamma is equal to minus s of x0, where x0 is equal to critical point of this function that we have 1/2 of s of x. Of s of x. So to find this critical point, we take its derivative, put it equal to 0, right? So if you take derivative, you get x minus g e to the x is equal to 0. So x is the value of inverse of this function that I'm going to write. So basically, here the equation that you get here is that you get x e to the minus x is equal to g, right? In order to find x0, we have to solve this equation in terms of g for each g, in other words. So if you draw the graph of this function, it's so this form actually, it has an inverse near zero. So this goes to zero, and then this function here is actually reaches the maximum at 1. It has an inflection point at 2. So at least here is invertible. Right? So, and then we just let f of g be equal to inverse function. So then what we have is that x0 is equal to f of g. Right? The solution of this one, it depends on g, right? So that we want to study this in terms of g. Okay, so then let us find the Taylor expansion of this guy, which is the Taylor expansion of the inverse function to that function. Proposition is that f of g is actually equal to sum n bigger than equal to 1, n to the power n minus 2 over n minus 1 factorial g. So I tell you, this is a completely a calculus problem now, because we have this function which is x e to the minus x, very clear. You can write this power series expansion. And what we want to do, we want to find the power series expansion of the inverse function. So that's a completely, it's just calculus problem, really. There's nothing beyond that. But it's quite an interesting calculus problem. I'm sure there are other solutions. But the solution that we get here using residue formula, okay? So, proof. Let us write f of g is equal to sum a n g m. I mean, for example, I believe you can use it, you can get this formula using inverse Lagrange inversion formula as a good exercise, but let me do it this way. That's in the book, actually. So we've got this n bigger than or equal to 1. Obviously, there can't be a constant term because the function is 0 at 0, so the inverse is also 0 at 0. So that's what it is. Then an, the coefficient an is equal to counter integral for small counter near 0. This is equal to 1 over 2 pi I f of g over g to the n plus 1 dg. I mean, this is Cauchy. I said residue, but this is Cauchy's formula in complex values. This is Cauchy's formula. Everything is holomorphic near 0 here. Okay. So then you can change variable. You get that this is equal to 1 over 2 pi I integral x, and here's a loop integral again, x e to the minus x to the power n plus 1 d of x e to the minus x. We are changing value from here. X e to the minus x. Okay. So you can evaluate that easily. This turns out to be equal to 1 over 2 pi I e to the nx. Simplify that, and we get 1 minus x over x to the n dx, which is equal to actually n to the n minus 1 over n minus 1 factorial minus n to the n minus 2 and minus 2 factorial. And that's equal to n to the n minus 2 over n minus 1. So this is the expansion explicitly of the inverse function f of g explicitly computed. So then we write down the critical point equation. Then basically it will be done soon. No, we have. This is the critical point equation minus s of x0, which is compute now, which is compute s of x0 equal to negative f of g squared over 2 plus g e to the f of g. You just differentiate this with respect to g, you get minus dvg s of x0 is equal to negative f of g prime of g plus g e to the f of g prime of g, and then 1 plus e to the f of g, which is equal to f of g over g. Comes out, simplifies this. So finally we get that yeah, so from here we get that negative s of x0, which is equal to integral from 0 to g by fundamental theorem of calculus. The derivative of this guy, we just use fundamental theorem of calculus here towards this, so we get f of g over g, because okay, so this is f of a over a dA. And if you do that, you get sigma n bigger than 1 and to the power n minus 2 over n factorial gn. So comparing this with the original formula, then you get that sum 1 over order of automorphisms of gamma. Gamma belonging to, this is the set of isomorphism class of unlabeled trees, because in Feynman's theorem we were dealing with unlabeled trees, summing over unlabeled trees. 1 over this is equal to n over n minus 2 over n factorial. Okay, so just n to the power over n factorial. So we get that. Now, if you bring it to the left-hand side and divide, sum over n factorial over order of automorphisms of gamma. Okay, now, how can you order an unlabeled tree with n vertices? There are n factorial permutations. I mean, there are n factorial choices of labels, but not all of them will give you different label trees. If 2 trees are isomorphic by the symmetry automorphism, you get the same label trees. So this indeed is just a set of isomorphism classes of label trees. That's it. This is, I mean, this is exactly the number. So the number of label trees. I mean, this always happens. Yeah, for each unlabeled tree, there are this many labeled trees that comes from that unlabeled tree by labeling vertices with 1 to n in different ways. And this is the Masoud system. Okay, so that's the theorem of Cayley that I wanted to prove. And I think it's a good time to stop now. Sorry I went over time. I wanted to build some momentum so that we just don't get bogged down. Are there any questions in the Zoom? Okay, maybe I stay. Okay, thanks very much. Then I see you on Wednesday, right?